we're using the combined gas law. So I'll read off the problem like I was doing before. I've already organized what we've been given, what we need to find, and then what equation we'll be using, right? So it's a gas, it says a gas has a volume of 675 milliliters. So there's my initial volume. It's at an initial temperature of 35 degrees Celsius, which I've already converted directly to Kelvin. And it told me its pressure was at 646 millimeters of mercury. Then it says, what is the volume? So that's my next volume, so I'm changing the condition, so V2, in milliliters of a gas at negative 95 degrees Celsius. So I've converted that already to Kelvin. And you can see where that problem's coming in, just like when we did, I think it was Boyle's law, when we had 0 degrees for Celsius. Now we have negatives. Having an absolute scale where the numbers can't be 0 is going to preserve this relationship. So we have to be in Kelvin, right? So there's our negative 95 degrees C in Kelvin, and a pressure of 802 millimeters of mercury. So I have all of this information plus what I'm trying to find. Well, how do I know I'm going to use the combined gas law? My conditions of constant number of moles of gas. So we have our combined gas law. So here, what am I trying to solve for? V2. So I can do a couple of steps. For one, I said you have the option of just dumping the numbers in and then solving. That's fine. I find it more intuitive to just isolate the variable I want first, and then dump the numbers in. So here, first step I'm going to do, let me get T2 on the other side of the equation, because I still want V2, right? So if I multiply both sides by T2, now I'll have P1 V1 T2 over T1, but that equals P2 times V2, and the only variable I want to solve for is P2. So if I divide both sides by P2, I'll end up with the equation P1 V1 T2 over T1 P2. And that equals V2. So I know for some people this might seem overwhelming right now. I have so many variables around. It comes with practice. It's actually not that bad. Don't let it intimidate you. You guys easily have the math skills to do this, right? So what I look here is ask, okay, do I know P1? Yes, I do. Do I know V1? Yes, I do. Do I know T2? Yes, I do. Do I know T1? Yes, I do. P2, do I know P2? Yes, I do. I have 1, 2, 3, 4, 5, 6 variables, but I know 5 of them. I can always solve for that last one. So let's add those numbers in and then see what we get. So I'll do my best to stay on the edge of the board. So it looks like there you guys can't see. So I'm going to come back up to the top. You can keep writing straight down. So if I put in my P1, which is 646 millimeters of mercury, times my V1 being 675 milliliters, times my T2, which is my 178 Kelvin. Making sure that's still on the slide. Good, we're good. Divided by T1 times P2. Well, T1 is my 308 Kelvin. And then my P2 is my 802 millimeters of mercury. So I've run out of space on the board that you guys can actually see. So I usually do the math right here and go over. I'm going to drop it down, but our final answer should be, when we do all this math, all of that is equal to 314 milliliters, right? This one is a little less intuitive to ask if it makes sense, because we're actually changing a lot at once, and in fact we're changing 2 things. So sometimes having an intuitive sense of how big the number, should it go up, should it go down, it's a little bit more tricky. So you're going to have to trust your math skills on this one. But in this case, given that I started under all of these conditions, I changed 2 of them. It's kind of hard to predict, but I still can calculate. And then that's the combined gas law.